last debate today, we have Dan Hashimoto and Andrew Hung, which will be debating on supervised versus unsupervised learning.
All right.
Oh, I guess I get to go first. Look at that.
Sure.
All right, well, thanks very much. This is a lot of fun, I think, to have a conversation around this topic. I'm going to cheat a little bit, and I'm going to expand my range a little bit outside of unsupervised to take what I call unsupervised learning and friends. So if we think about the spectrum of how we train machine learning models, particularly with clinical data, you have a range of learning technique going from truly unsupervised all the way to fully supervised, which we've seen some of the talks already go over some of these supervised techniques and how they achieve what it is that they want to do. And within those learning strategies, you have certain example strategies within those, right? So within unsupervised learning, you can consider self-supervision, where really all of the labels are extracted from the text itself. I was having breakfast with Tony this morning, and he kind of reminded me, right, large language models that we've all seen through ChatGPT and things, some of the initial way that happens is just purely sort of looking at the data, what word comes next based on association within the data set itself. Then you can move on to things like distant supervision. Can you use a different source to infer labels for the data set of interest that you have? And then starting to move into the semi-supervised categories where you might have weak supervision or noisy labels where you're not going to have this really clean, hey, let me tell you everything you got to look for and what it looks like, but let me give you an aspect of that and I'll show you an example of what that looks like. And then moving forward toward active learning and then fully supervised learning where a clinician hopefully or some other human being has had to manually review all the labels on which an algorithm is trained. The problem with something like supervised learning, however, is that Dan Donahoe made the point earlier, it's very difficult to get clinicians to label your data. It's very difficult to have people sit there for 20 minutes at a time even, and that's nothing compared to an operation that can take 3 hours, 6 hours, 8 hours, depending on the type of surgery that you're doing. And so far, the techniques that we have utilized have been addicted to frame level supervision. Right? Every single image within a video gets labeled for what organ is in there, what instruments are in there. So you have a very good idea of what is the ground truth, but it's come at an incredible cost, right? And so people have tried to move toward other paradigms, thinking about, for example, these weak supervision elements, where you can say, okay, well, in this video, you have this particular instrument, let's say the hook in this example. And that's predicated, though, on the understanding that you have constant object presence, which means that hook has to be there throughout every single frame of the video if you're going to infer that it's in every single frame. The reality of surgery, though, is that we deal with a transient object presence problem. Things are coming in and out of the screen, and that makes it very difficult. But you can leverage some of these types of approaches to cheat a little bit on your problems, right? So on the bottom here is an example of a weakly supervised transient object presence problem where if you just have it in the video, this is work from one of my postdocs, you tell it, oh, there's a hook, there's a grasper in the video, it's going to come in and out of screen, I want you to find me all the instances. And we actually do fairly well. You can actually see the segmentation that it generates on the far right. But the reality is that at least in computer vision problems, unsupervised learning approaches or sort of these weak supervision problems are still relatively in their infancy. Where we've seen better examples of this is in risk prediction around morbidity, mortality, drug discovery, utilization, where we see examples, for example, about how do you cluster patients based on the data that you have. This is a project looking on risk factors or risk prediction around mitral valve surgery, looking at things like phenotypic and genetic variables, where without a clinician having to go in and say, hey, these are the things I want you to look for that are high risk to me as a clinician when I conceptualize this problem, they were able to use unsupervised approaches to describe 4 clusters of patients. Now, some of them are going to make sense to us as human beings, right? Older patients with heart failure, with arrhythmia, who have had a prior stroke. Those are going to be at the highest risk of mortality in cluster 1. Well, that's obvious probably to us. And but group 2, which is the youngest, they're multi-ethnic, but they're obese. Those have the highest risk of major adverse events. Again, some of those elements fit, right? Obesity and things like that, but others may not. Why is it when they're young? And if you look at that second row across, they tell you the genetic variants. I don't know anything about gene RS948552. That means nothing to me as a clinician, right? But when you have that data and you can cluster together around some of these outcomes, you can find interesting patterns. And that's why I think there's a value to unsupervised learning, because if you're looking at a paradigm of what we know and what we don't know, supervised learning really fits you into this top right square of known knowns. Right, you got to know what you're looking for. And you're leaving all this other stuff on the table around what's unknown, right, that you know you have to go looking for, and what are the unknown unknowns, things that you don't know you have to look for. Now, this sort of paradigm comes from a former Secretary of Defense in the United States who wasn't that great, but I think it applies very well to what we're trying to talk about today. And so just to close that quickly, in supervised learning, if you can see it, you can find it, but that doesn't leave much room for imagination or what we want to do. And since it seems obligatory to reference Ferrari while we're here, I took my son there yesterday, and there's a quote from Enzo Ferrari that if you can dream it, you can do it, which I think is sort of what unsupervised learning finds into, which is if you have to think about, you don't have to see the example of, aha, this means this. Because there are ways of interpreting data that we as humans can't quite comprehend, and we want to leverage the power of these computing infrastructures and these techniques that all these brilliant engineers in the room with us here are developing to really unlock new ways of thinking about medicine and thinking about how we deliver care.
Awesome. Dan's very charismatic and convincing, so I'm not sure about this. So the next 5 minutes will be how I've justified, will be justifying what I've done for the last 10 years of my career. So in supervised learning, you're working with labeled data, and I'm going to argue that especially in the realm of surgery, you have to work with labeled data. You're working with data that is grounded in clinical relevance to then plug into models that are going to be used to predict things that are clinically relevant. So our team, this was several years ago, wanted to come up with an assessment tool for suturing technical skills. And in order to have this final product of this tool that would be used to assess the granular performance of a surgeon while suturing robotically, there was a first step of a cognitive task analysis where we brought in 5 expert surgeons plus an educational psychologist to break apart suturing down to its nitty-gritty, to all the really fine details of what makes suturing good or bad. And then over the course of several months, we came up with a set of principles that we then gave to 16 surgeon panelists, and this group worked over another 3 months to finally come up with this assessment tool. And this is what that tool looked like, where this is only half of it, but going down its main domains within suturing, and then within each domain there are sub-skills. For example, for needle handling, it is about how the surgeon holds the needle, in what ratio along that needle, the angle to which they hold it, the depth within the grasper that they're holding it at, and the number of times the surgeon's having to re-grab or reposition that needle. Those all fit into just the domain of needle handling. And each cell, so looking down on the vertical columns, there's an ideal example, there's an adequate example, and there's a fail. So to fulfill the criteria for each of these things, we created objective descriptors or criteria of how you would score in all of that. So the idea here is that these are one of the criticisms of a skill assessment is that it can be a subjective assessment, but here we've really made it objective. And so the quality of assessment is grounded by the clinical science behind it, but the labeling of examples of good suturing or poor suturing also goes through a very rigorous process. We don't want to make any errors. And so for every example, and someone's going to say something about sustainability and so forth, but what we've done is for every clip of suturing that we're assessing for a particular skill, we've had 3 evaluators look at it. And they can actually go through them pretty quickly. Now, example 1 is where you have 3 raters. They watch a video, and everybody rates it as good, 3 thumbs up, so then that's your final label. Now, there are instances that your 3 raters are not going to agree. The minority score will rewatch that in a round 2 that's individually done, and they have an opportunity to change their mind after re-review. They decide that it's still a poor example of suturing, so then it goes to a group review. Everybody reviews it, and by peer pressure or whatnot, they've now all agreed that it was a good example of suturing. But there are also opportunities where they on individual review, This is example 3, where you have 2 raters that rated it as poor, 1 rated it as well. The minority rater switched his or her opinion, and then you have a final label that's a poor example. So this is an example of where we wanted to really streamline the process of labeling while not making errors, and so we provide that opportunity for individual review. The group reviews are really where it's very resource intensive. And then finally, the last thing to say is with these relatively large labeled data sets, we are then able to train these models that, as you saw in my prior talk, be able to identify surgical movements as different gestures, or to identify different examples of suturing as high skill or low skill in a very granular sense. And this is only possible because you have informed this model what is good examples and what are poor examples. And without that, how could you possibly have that clinical impact that we ideally want to have? So finally, I harp on the clinical relevance piece because that's what surgery is all about. It's knowing the anatomy, it's knowing how to do the procedure, it's knowing what connects the dots to a good outcome. We do go through the way we've done it in my group is a very rigorous, although time-intensive process, but we've streamlined it to minimize error. And finally, having label data, I think you ultimately need less data for more efficient learning.
Doesn't that sound so tedious? Who wants to do that? No, but I think like everybody else, I think we're all kind of on both sides of the same coin. I do think you get that clinical sort of impact element, and you get something that you can trust, right, which becomes so important. But to fit back in my debate hat, you get sort of more efficiency with less data, but can you generalize out of that, right? Are you stuck into this narrow paradigm of here's what I trained on, and then how do I, make sure that these models can then generalize outside of those specific scenarios?
Yeah. Only because Dan and I are friends, and we're all winners here. This particular model that we have is one that is pre-trained in an unsupervised manner, right? So with everyday objects. So ultimately, down the pipeline, we're looking at assessing surgeon skill through video. But these models are pre-trained on everyday objects in an unsupervised manner, and then fine-tuned with clinically labeled data, of course, to make the insights. And without that foundation model that is generalizable, you can't do the downstream steps. Now, it's an open question whether or not having foundation models that are trained on surgical videos, for instance, will that augment performance? This is something Oz was talking about earlier this morning. That remains to be seen, but it's, again, one of those situations where we want to harness both worlds to really get the best impact at the end.
Maybe building on that, one question kind of back to both of you is, we've seen at this conference many examples of it through the talks. We've seen the live surgery. There can be complexities and variability associated with surgery. And then depending on the problem you're trying to solve, you may want to go deep on very infrequent things that happen, or you may want to up-level the average surgeon on most average things. Can you comment on how each technique might be suited to solve that problem of complexity and variability in surgery?
One of our greatest challenges is for certain things that we look for, people rarely do poorly on. But if they do poorly on, those are the test cases. Those are the cases where you do really want to improve on. But at least in the supervised training world, it's a huge challenge when you have rare examples of something and you're just really stuck with it, because you have that class imbalance where you really, ideally for training these models, you want to have a balance of the good and the poor. But if the poor examples are so rare, it's just very enormously difficult to train.
I think you run into that same problem with unsupervised approaches too, because at the end of the day, you still need data to reflect some of the phenomenon that you're looking for. And so it's a problem, I think, for both approaches. I don't know that you're going to solve one with the other or vice versa. But it's true. I think that, as much as we talk about making surgery safer, surgery is very safe, right? The complications that we're looking for are 1%, 2%, which is probably too high because we want everything to be perfect. But when you're talking about trying to train models to look for these things, this class imbalance problem really sort of throws a wrench in the works when we're trying to find these like events that are going to happen once or twice out of every 100 cases, if even that much, right? So.
But that may be the plug for, some of the things like Dan Donahoe's doing with the collective, and all of our projects are multi-institutional. It's with these sort of multi-institutional efforts or through industry where you are able to aggregate data. That's one of those really important initiatives or vehicles to be able to not be stuck with these rare examples where in one given institution it only happens once a year or so often, where you can actually aggregate these rare instances and be able to learn from that.
Which is a plug for everybody in this room to collect your data, right? So if you're a clinician and you're not already collecting your data, I would highly recommend that you do that, because I've talked to surgeons who are like, oh yeah, I saw that one time. Yeah, I didn't record it though because I didn't think I was going to see that, right? Or I didn't think that was going to happen. And so just getting into the habit of collecting that data as you go. And I say that for video data, but really it can be multimodal. And there's no shortage of people, both from the engineering world, the surgical world, and industry, that can help you do that if you're at this meeting, which is nice, walking through the hallway and seeing all the technology there. So I'd encourage you to look into that.
Oh, last question, actually. How do you see the value of using synthetic data, whether it's with Gen AI or digital twins or a combination of those, to basically help you fix the imbalance that you have with those rare cases?
Yeah. In theory, it's a great idea, right? Because it solves that gap. An open question I have is, ultimately, is it going to help us? So from a quantity standpoint, on a spreadsheet, you see that now suddenly that rare example you have, now you've balance things out, and on paper it looks great, but is that just a little band-aid, or does that ultimately allow us to make the clinically relevant insights? So it's an open question. I'm certainly open-minded in that regard.
Yeah, I think I agree with that, especially if you look at some of the things like Mihaela van der Schaar's done and things like that in synthetic data generation. Sure, you can augment these rare examples, but then you're just perpetuating these biases that are built into the rarity of that. So now you can, as Andrew said, you can make your spreadsheets look better, you can make your numbers look better, but then when you go live for clinical application, the reality is the real world incidence of that problem is not going to be that class balanced sort of setup that you've artificially created. So is that model going to work appropriately? And even if it does work, what biases were in that initial data that you've augmented, whether it's a digital twin framework or whatever, that are now going to be perpetuated out and could potentially impact care in ways that we can't predict. So it's just a sort of that cautionary tale too.
All right, well, this was fantastic.